In ionic bonding, okay, why are the atoms held together? What makes the two atoms stick? Charges. One is positive, one is negative, and the positive and negative stick together. It is formally called an electrostatic bond, kind of like static cling, okay? And so the charges are holding them together. The larger the charge, the stronger the hold, okay? And so if you by chance have, let's say, 2 plus 1s, then they stick together. But if you have 2 plus 3s, or a plus 1 and a minus 1 sticking together, and a plus 3 and a minus 3 sticking together, you would think that the one with the larger charges are basically stronger magnets and they're holding together. That's what we're going to show you as we look through the energies involved. Okay, so we've got to make one a positive charge, a cation. We have to make one a negative charge, an anion. We learned 2 trends about making charge, okay? And those 2 trends were ionization energy and electron affinity. Ionization energy, the energy necessary to take an electron away, and the electron affinity is the energy that is given off when an electron is accepted. Now here's what happens. For a reaction to proceed, energy, when you add them all up, must be negative, or it must give off energy. What has to happen is whatever you start with has some sort of energy. Whatever you end with must release energy because what has been made is more stable and energy has to be given off. Okay? And so we all know that sodium chloride salt, table salt, exists, right? Now, I showed this slide earlier, but you may not have noticed something. All right, take a look at this. The energy necessary to take an electron away from sodium is 495 kilojoules per mole. It's an energy value. What's important? Large positive. It costs us a lot. Now, what's going to happen is the chlorine is going to accept electron, right? There's the value, negative 349. There's something that doesn't add up right. If I take positive 495 and negative 349, I put them together, the answer mathematically will be positive, saying that that reaction will not come together. So there must be something involved that helps in this reaction. Now, remember, the ionic compounds are put together, and we're going to see this is different when we look at molecular compounds, but the ionic compounds are put together in repeating lattices, repeating units. So for every sodium, there is a chloride. For every chloride, next to it is a sodium. And it creates this large block, kind of like Legos, put together. Now, there is an energy in this organization of the lattice, and that's what we haven't accounted for. We've accounted to make it a cation, we've accounted to make it an anion, but there is a lattice energy. That's what we're going to talk about. And so if I take a look at sodium plus chlorine, the actual value is minus 410. And that isn't what we would have mathematically calculated the slide before. And so we can talk about ionization energy, how much it takes, which then converts that atom from 11 down to 10, or completes the octet by taking away the 11. And then the affinity we talked about, by filling the octet of chlorine, it still doesn't become negative. Okay? But the reaction is extremely what they call exothermic, or gives off energy. This number is very, very good in terms of gives off lots of energy, becomes very stable. Where is that energy coming from? It's coming from this arrangement and this lattice where everything is organized. And so in the case of sodium chloride, every sodium is surrounded by 6 chlorines, and every chlorine is surrounded by 6 sodiums on the inside. Now the edges, that's not true, but the majority of the atoms are in the inside. This stable structure produces a very large amount of stabilization. Gives off lots and lots and lots of energy. Okay? And to break it apart, I would have to add that amount of energy, but this stability comes from this lattice. Now we can actually mathematically calculate that using this very nasty equation. Actually, it's not that nasty, but it is something that I am not going to actually make you mathematically calculate. I'm going to explain this equation and give you some rules by which we do it. But I can actually calculate an energy if I use this constant right there, and then I use the actual charge of the first item, the first element, and the actual charge of the second one. So if I take the actual charge of the value of the cation and the actual charge of the value of the anion and place them in there, that is part of the equation. There's one more item, and that's this in terms of distance. Now, why I won't make you do this equation too often is this. What charge does sodium become? Answer me that. Plus what? Plus 1. Now, we do that and we say that it's plus 1, but that is not its charge. The charge was determined in the experiment called the Milligan's oil drop experiment, where we shot electrons at oil and they fell through two plates. We turned on the electricity and they either slowed down or stopped or started going up. We actually calculated the value of the charge of an electron, which is actually equal to the charge of a proton. And so we would actually have to use that actual number, the mathematical value of charge. But for us, we've used charge that says we have one of those charges, minus 1, or one of those charges plus 1, or we say we have two values of that charge, plus 2 or minus 2, or three values of that charge. And so we have talked about plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. And so that's why I'm going to teach you how to interpret this equation using those terminologies. And so if you take this equation and you do this, if I compare two things, if by chance I compare this, a plus 1 and a minus 1, okay, 1 times 1 is 1, right? Okay, compare that to an example that I would have a plus 3, a minus 3. 3 times 3 is 9, right? In this case, I'm going to eliminate the charges, and I'm just going to say 1 times 1 is 1. So the value of energy would be times 1. And if you had charges of 3, the value would be 3 times 3, 9. It would be much larger. So the energy is much, much larger the larger the charge that you have. Okay? And so that is important. Also, there is one thing that you would have to watch out for, okay? What happens if you get this comparison? You get a 2, and you get a 2, so a positive 2 and a negative 2 come together, two atoms, and you compare it to a 2 and a 2. Some other atoms that have a plus 2 and a minus 2 come together, how would you determine the difference between those energies? Okay, that's when you get to this part right here. If by chance you have the same value of charge on the top, then you have to look at the bottom, and that says distance. And what happens is this: if you're dividing by distance, the smaller the distance that you get, the larger the energy. So in this, the smaller the distance, the larger the energy. And the larger charge, the larger the energy. And that's what we're going to look at. Without having to do mathematics, we can say the more charge on the top, more energy. The smaller the distance on the bottom, more energy. The charge wins out, though. The charge is the biggest influencer. Okay? Doesn't matter if you have 1 and 1 charge versus a 2 and 2 charge, the distance will never be enough to overcome making the 1 and 1 bigger than the 2 and 2. Okay? So if we take a look at these and we want to use that rationale, okay, then we need to look at charges and distances. Okay, so if I look at these two things, all right, sodium is what charge? +1. Fluorine is what charge? -1. The cesium is a what? It's a what? +1. And the iodine is a -1. And the calcium is a +2. And the oxygen is a -2. Okay, which one is bigger straight off the bat? Calcium oxide is much bigger than, okay, what about the other two? Okay, I look, they both have the same charge, right? So now I have to figure out which one, about the distance. Now, do we know distances? We know trends of the sizes of atoms. And so, which is larger, cesium or sodium? Cesium. So this one is larger, this one is smaller. Let's look at it. Is iodine or fluorine bigger? Iodine. And fluorine smaller. Oh, stop. Okay. And so if I look at these, sodium fluoride is smaller. That means the distance is smaller between the two. That means the positive and the negative get closer. Okay? And if the positive and negative are closer, then that's on the bottom of the equation. So this one becomes larger than this one. Both of these have the same charge. Okay? These two have the same charge, but this one is smaller in distance than this last one. We take a look at the trends here. Okay. As I go down here, what happens? All right, lithium, and then sodium, and then potassium, and then cesium. If I go and I look down the row, lithium, sodium, potassium, and cesium, cesium is huge. That means its distance is big. That means the energy goes down compared to these. These are all +1, -1s. And so as we see this change in distance, we see the energies tend to go down. All right, take a look at this. Magnesium and chlorine here. Now watch this. This is a +2, and then I have 2 -1s. Look at the energies involved here. Less than 1,000 or right at 1,000. Look at that, 2,000. Much larger. But look at this one. A +2 and a -2. With this being a +2, that being a +2, that's similar. But here, this being a -2, and this being 2 -1s, the charge is the same, quote unquote, but this is one atom that has a -2 charge. That is better than this one that has 2 -1 charges. And you can see the energies really increase. And if I get a +3 and a -3, the 3's really overcome. Okay? So, principle. The larger the charges, the more intense the charges on each one of the atoms, the bigger the energy. And the larger the atoms become, the less energy, because it is on the bottom of that equation. You will have an exam question, probably something exactly like this, okay, for you to think about. And it will have different charges, and then it will have some that have the same charges, and you'll have to distinguish between those that have the same charges. Okay, so using those rationales about what that equation. I will not make you on the exam calculate a value, but I don't know, CHEM-111 could make you do it. what you would have to actually do is look up the value charge of an electron and use that actual number and multiply it by 1, 2, or 3, depending upon what your charge is, to actually calculate the value correctly on a CHEM-111 question. And so it could be there. I don't know. All righty. At that point in time, what happens on Monday? An exam, okay? And so looking at an exam, all the material, if you've viewed the online lecture, all the material has been lectured for that. I do want to cover just this really, really quickly, okay? This is a tool. Booger. That's the wrong thing. I think I handed out the wrong thing. Should have one that looks like that. Let's take that back. This thing printed out weird. That one. All right, that's it.
Is it hard to record an answer?
Hmm?
Is it hard to record?
Yes, it was. It was really, I tried to find something that was quiet, and I could not find it. It was ridiculous. Yeah, it was a real stressful weekend for me. Exactly what I had intended. All right. Just thinking about naming compounds, there are 3 kinds of compounds that you must name. What are they? Ionic, covalent, and then acids. Okay? Those are the 3. All right. How in the world do you know what to do? All right. Well, there are rules for each one of them. Okay? There's separate rules for ionics, which is totally different than moleculars, which is totally different than acids. So what you have to do is figure out which one scheme you've got to use. Enough. All right. Do you have an extra? No.
It's probably
But okay, I'm running out of 1 sheet. Okay, there's 3 sheets that make up a whole set. All right. That is 100, and that's a full set on 3 sheets. I'll upload those single sheets. That's a full set. And then individually. All right. Everybody gets something. All right. Here we go with this. How in the world do we think about naming these compounds? Here's the deal. When you look at compounds to the name, you've got to decide what 3 different schemes you're using. And so, Actually, this becomes a question that can be done in the exam by itself. You have to identify, is it molecular, is it ionic, or is it an acid? To do that, we simply look at the first element in the compound. All right? So if I start in this box with the first one in the right, if I look at that element's name, it's calcium. Okay? Is calcium a metal or a nonmetal? A metal. Okay? And it's not hydrogen. So if it is a metal, what kind of nomenclature do I use? What kind of compound is that? Ionic. Okay? And so in this naming scheme, okay, when I look at that first metal, look at that first element, okay, and it's a metal, the exception can be the ammonium ion, okay? Then I have to use the scheme in which I have to name the cation, and then I have to name the anion. The cation can be easy because it's the name of the metal, okay? But we have to decide, is there anything extra I have to put with it? So for the cation, is it a transition metal, tin, or lead? Okay? If it is neither one of those, then you just use the name. In that case, calcium, is it a transition metal, tin, or lead? Nope. So then I use the name calcium. That's its name. I have completed the cation. Then I have to look at the anion. Is it an element? Just a single element in your example there? No. So it's not an element, so I have to use this. It's a polyatomic, a group, and every group has a name. So what is its name? Cyanide. So the correct name for the first is calcium cyanide. Okay. I'll do the next one. It starts with iron. The first element is iron. Is that hydrogen? Is iron hydrogen? You better get this one right. It is not. Okay. Is it a metal? Yes. Okay, so we're in this scheme again. So the cation is iron. Is iron a transition metal? It is a transition metal. Okay, so I have to go over here. Use its name, iron, and use a Roman numeral for what? The charge of that element. Now, it says FeCl2. You can determine this two ways. FeCl2. Okay? You can either do this. 2 goes up, and the first one's always a cation. You can do that. Or you usually know what the anion is, which is a -1. I have 2 of them, so this must be a +2. So the element's name for this one would be iron, parentheses 2, because that's the version of iron I'm using in this one. I have completed the cation. I now will go the anion, and if I look, is this an element? Yes. The name of the element is chlorine, but when I name it as a compound, chlorine becomes chloride. Okay? And so that second example, FeCl2, will be iron 2 chloride. This example here, CO2. Okay? Its first element, is it hydrogen? No. Is it a metal? No. It's a nonmetal. So I've got to use this scheme. This scheme is for what we call either the molecular compounds or covalent compounds. They're interchangeable if we use both of those terms. I named the first element. Okay? What is the first element here? Carbon. And I add a prefix to determine how many there are. The special rule for the first one is don't use which prefix. You never use mono on the first one. So it becomes carbon. Okay? The second element, you have to add the prefix, whatever the number is, it must have a prefix, and the ending must be changed to "ide." So the element is oxygen, but it becomes oxide, and in this case, how many do I have? 2, and the prefix is dioxide. Okay? Name for me this. This is a really weird one. Dihydrogen monoxide is its official name. Do we ever say that? Only if you're being cute. What is the other name for that? Water. It has a common name. There's a couple things that have common names that we use. All right? Last thing. This one. Hydrogen, nitrogen, oxygen, that has 3 of them. Okay? Does this start off as a hydrogen? Yes. That's going to be within the acid grouping. Okay? The acids depend upon and only depend upon this part right here. Okay? And so what is the NO3 ion called? Nitrate. Okay, that 8 is what is going to dictate. Okay, if I have an 8, I change it to ic acid. Okay, and so this one would be nitric acid. How would the name change this way? What is the anion here? Nitrite. And so it becomes nitrous acid. Okay? What if I have a element with an "ide" ending, like bromide? What do you put in front of it? Hydrogen, hydro, and this one would be bromic acid. So hydro in the front and ic acid at the end. So what is this name for HCl? Hydrochloric acid. You may have known that just by thinking that it was a common name. It isn't. It's actually a formalized name where I put the hydro in the front. Chloric acid is the formalized name for that. Although we use this so often, some people memorize this as a common name. And so if it starts with an 8, it becomes an ic acid. If it has an nitrite, it has an ite, it becomes an us acid. And if it has an ide as the cation, it's hydro in the front and ic acid at the end for the nomenclature. Okay? And so, looking at a group of compounds to name, the first thing is you have to decide which scheme do I use. Do I name it as an acid? Do I name it as a ionic compound? Or do I name it as a molecular compound? Never mix the two up. Okay? You're either going to be using di, tri, tetra, that's all one, or you're going to use parentheses, but never mix the two. Okay? You have to decide which scheme you're using before you start naming things. All right. Okay. Molecular geometries. Start of a brand new test. Okay, so this is not something that is going to be on our test, although it's going to reinforce a lot of the concepts. You'll have to know the concepts for Chapter 5 to really kind of do Chapter 6. And so, even though it's not on the exam, the individual information, they're kind of so ingrained that a little bit of 5 is going to be on test number 6, a little bit of, it just, the material is just so put together. All right. What we're going to do is look at molecular compounds and how they're put together and those bondings. Ionic compounds are very simple. Positive, negative stick together, big lattice. Okay? Not as complex, but molecular geometries really tend to be a lot more complex in terms of what could happen. Although molecular geometries are quite a bit more important because they mimic the kind of structures that are in your bodies and how our proteins work and how drugs are made. And so a lot of the compounds that come out of the molecular and how we look at them in the three-dimensional shapes are the important things of life in a lot of ways because of that. So understanding this can give us insight into how the body actually works. And so we need to understand how those make three-dimensional structures. So we're going to go from writing it on a piece of paper to what it looks like floating around in three-dimensional space. That is the big step in this chapter. Okay? What we're going to do is we're going to draw what are called Lewis structures. Now, remember we had Lewis symbols? What did the Lewis symbol represent? If I put, let's say, X, what do I put around the X? Valence electrons. And so if I had 5 valence electrons, 1, 2, 3, 4, 5, I would have 1 bonding pair and 3 individual electrons. Okay, so we're going to use something like this, but we're actually going to draw how the molecule actually looks. Okay, so what's important is in the Lewis structure, we have to have and know the Lewis or how many valence electrons. And we have to account for every valence electrons in this structure. The important part of this is we're going to try to fulfill octet or having 8 around. So in any molecular molecule that we're given, we have to add up all the valence electrons that are asked of us. If there's an ion, we have to account for the charge. That means if it's plus, take away an electron, and if it's minus, add how many electrons there are. Identify the central atom. Usually it's written first. Most likely it's the least electronegative. All right. Third, once you've identified the central atom, you make 1 bond to all the other atoms that are in that compound because they have to be connected. And we use 1 bond, which is 2 electrons, to bond each. At that moment in time, we have to then fulfill octet around every atom on the outside. The exception is hydrogen. Hydrogen octet, or its closest noble gas, only has 2 electrons, so it only can accommodate 2 electrons. At the end, after we've drawn all of those and fulfilled octet around everything on the outside, if by chance you have extra electrons left, put them on the central atom. Then you have to check, does everything have octet? Well, if you've checked everything on the outside, that means you have to check the one on the inside. It may or may not have octet. If it is less than octet, then what you do is you take a lone pair and you throw it in to make a double bond or possibly a triple bond to try to get the central one up to an octet. And once you have gotten it up to an octet, you're done, okay, in the initial drawing. I'll then teach you another set of rules to check your drawings. Okay? So if I take a look at this particular compound, all right, name it. What is this compound's name? Phosphorus trichloride. Okay, great. You've just gotten chapter 5 done. Okay. All right. We have to find out how many valence electrons are in this compound itself. Okay. For the phosphorus, it is 5 valence electrons. Remember, only S and P are the ones that we're dealing with. In the chlorine, how many valence electrons do we have in chlorine? Each one of them. 7 times 3, pull out your calculators, is, and 7 times 3 is 21, plus 5. When you draw this, you have to take into account 26 electrons, okay? Before you do anything, you need to know how many electrons you have. This is neither a cation or an anion, so I don't add or subtract any electrons. Okay. And so, I would draw phosphorus as the central atom, and then I would connect one bond to each of the other atoms. Started with 26. At this moment in time, how many electrons did I account for? 6. How many do I have left? 20. Okay. What is my next step? Electrons on the outside, I have to get up to octet. So this has 2 around it, this chlorine, so it needs 1, 2, 3, 4, 5, 6 more. And then 1, 2, 3, 4, 5, 6. And so if I take a look at this chlorine has 8 around it. This chlorine has 8 around it. And 1, 2, 3, 4, 5, 6. How many electrons did I use when I did this? I've used 18. I have 2 left. Okay? And so, there I filled out what I just left. I have 2 left. And the 2 go where? On the central atom. Now, at the end, I have to check. Does phosphorus have 8 electrons around it? It has these 2 and those 2 and those 2 and those 2. It has octet. At this moment in time, every electron is accounted for. Every atom has octet. You would assume that this is the correct. It should be pretty correct at this moment in time. Didn't violate any rules that I wanted to have happen. And I have a Lewis structure. Okay. This is still, though, flat on a piece of paper. But it's going to give me enough information to tell me what it really looks like in real life, in 3 dimensions. We're not there yet, but I have enough information now to actually make that jump. Okay. All right. If I take a look at this one, okay, hydrogen had 2 electrons. The carbon had 4. The nitrogen had how many valence electrons? 5. I add those all up, get 11. Is that true? 2, 4, 6, 8, 10. Wait. Hydrogen does not have 2. Hydrogen has 1. It has 10. Okay. There. That's good. That didn't look right. Okay. Hydrogen has 1. Carbon has 4. Nitrogen has 5. Has 10 valence. So I did carbon as the central atom. I made 1 bond each. Okay. And making 1 bond each is 4, so I have 6 left. Hydrogen has 2 electrons, so it's fulfilled its octet. Nitrogen, I put 2, 4, 6. You 6 have 0 to put on the central atom. Nitrogen, wonderfully octet. Carbon, wonderfully octet. Carbon, does it have octet? No. So what I can do is I can take these 2 pair of electrons and put them in to make a double bond. But that would make it look like this. H, C, double bond in with 4 pairs of electrons. Does carbon have enough? The way I wrote it here, I have 2, 4, 6 electrons around carbon. That doesn't make it. So then what I can do is take a pair of electrons, throw them here. If you take a look at the nitrogen in every case, here has 8, here still has 8, has 2 in the bonds and 2 lone pairs, and nitrogen still has 8, 3 bonding and 1 lone pair. So nitrogen has not changed its rules. But what I've done is here, carbon has 4 around it, here carbon has 6, and in this version, carbon has 8 around it. So this is the Lewis structure that I would deem to be correct. Everything has fulfilled its octet, hydrogen with 2. And so you use double bonds until you get up to octet. Sometimes it stops at 2, sometimes it has to go all the way up to 3. Okay? And so that's what the compound should look like in its Lewis structure. Now, difference between single, double, and triple bonds. Okay? If you have one electron pairs, you're sharing 2 electrons, it is a single bond represented by 1 line. If you have 2 electrons that are shared between the atoms, it's 2 lines, or a total of 4. And if you have 3 lines, it's a total of 6 electrons, and it's triple bonded. Now the distances, a single bond, if by chance I'm holding my wife's hand and we're just holding one hand, we can get kind of far away. Okay, so single bonds are pretty far. And if we played Red Rover, someone could run through and probably break that bond pretty easily. But if I took my wife's hands, 2 hands, I've got to be closer to her. A double bond brings you closer and is stronger. Red Rover, compared to anybody that's holding one hand. If I'm holding 2, they're not going to get through, right? And if I held 3 hands with my wife, okay, it'd be weird, but I would be even closer and even stronger, okay? And you can think about having the 3 bonds like 3 strands, not quickly torn apart. The more that we are bound together, the stronger we are. Here's a Lewis structure, and this is the what ion? TRQ in real life. What is it? Oh. Let me write it the way that you would normally see it. Oh, you need to start working on some TRQs then. Bro. This is the bromate. Okay, the bromate ion. If you put one more on it, it's the hyperbromate. If you take one away, it's the bromite. And if you take 2 away, hypobromite. Yes. Okay. Now, in this case, that is the ion. All right. If there's an ion and you had to throw in an extra electron, we use a bracket and we say somewhere in there, there's a -1. Okay. So if ever you have an ion and you have to write the Lewis structure, you have to say somewhere in there is the charge. Okay. And in a little bit, I'll actually allow you to actually calculate that charge and where that charge actually resides. And anions, you add electrons, cations, you take away. So let's draw these structures. Okay. And let's say if they are polar or nonpolar. All right. Iodine bound to iodine. What is my first step for that? What must I do first? Know how many valence electrons. Iodine brings how many valence electrons to the party? 7. I have 2 of those, so I have 14 electrons to deal with. That doesn't even look like a 14. 14 electrons to deal with. What is the central atom? Trick question, right? There's no central atom because there's only 2, and it would be iodine. And then arbitrarily, I'm going to put 1 iodine on there. In this step, how many electrons have I used? 2. I have 12 left. Okay. Then I fulfill octet on the one that's on the outside. 1, 2, 3, 4, 5, 6. -6, I have 6 left. Then I go back to the central atom, in this case, the iodine, and I put all the electrons that are left over on that one. 1, 2, 3, 4, 5, 6. And I've used 6 electrons. I have 0. Does every atom have octet? Yes. This is a good atom. All right. Let's try this next one. Oops. the ammonium ion. Okay. The ammonium ion, the nitrogen brings how many valence electrons? 5. The hydrogens each bring how many electrons? Oh, bugger. Stop. There. Okay, good. Each hydrogen brings what? 1 times 4 equals 4. And the positive does what? Takes away 1. So 5 plus 4 minus 1 equals 8. So I have to account for 8 in this one. What is the central atom? Nitrogen. I have not used any electrons at this moment in time. My next step is to draw a line to each atom on the outside. Okay. How many electrons did I use in that step? 8 minus 8 is 0. 0 electrons go onto the central atom. Look around. Does this hydrogen fulfill octet? Yes. Does this hydrogen fulfill octet? Yes. All the hydrogens fulfill octet. What about the nitrogen? Does it fulfill octet the way I've drawn it? Yes. Have I written a good structure? Absolutely not. I have not put the bracket to say that somewhere in here I have a positive charge. I have now written a good structure. Okay. Carbon brings how many to the table? How many valence electrons? 4. Oxygen brings how many each? Not 2. 6. 6 times 2 is 12. I have 16 electrons to choose from. Central atom is carbon. Make a bond to each atom. I have used 4, have 12 left. 1, 2, 3, 4, 5, 6 to fulfill octet on that one. 1, 2, 3, 4, 5, 6 minus 12. I have 0 electrons to go into the central atom. Does each of the oxygens have octet? Yes. Does the carbon have octet? No. What do? Cry? I double bond. Okay? If I take one of these lone pairs and I stick it there, oxygen, double bond carbon. Am I there yet? Okay. What can I do at this moment in time? I can do another double bond, or I could do a triple bond. In this case, there's a reason why. I'm going to do a second double bond. Try to invoke double bonds rather than doing triple bonds before you have to. Does carbon now have octet? Yes. Do each oxygens have octet? Yes. This would be a good Lewis structure for that compound. Okay? All right. We have finished up. I will see you next time.